I'd like to introduce Cheng Shao, our next speaker. He is a software engineer at Tweag, where he's worked since 2018, right?
Yep.
I remembered correctly. One of his major contributions has been originally the Asterius Haskell-to-WebAssembly fork of GHC, which has now been re-architected and rewritten and integrated into GHC itself. So we now have a WebAssembly backend. And yay! And in addition to continually improving the WebAssembly backend, Cheng also does work on sort of low-level code generation-related tasks in GHC as part of his work. So thank you all for paying attention, and thank you for speaking here.
Yeah, thanks all. So before I go to the prelude slide, which does self-introduction and lay out the agenda of this talk, let me present to you this build instruction for the GHC WASM backend. So some of you can probably kick off a build on your laptops already while you wait for my introduction later. The simplest approach, which is sort of became the official recommended approach, is to use ghc.next. If you have Next installed on your environment already, the way to use ghc.next to build the GHC WASM backend is as follows. There is a flake option called with WASI SDK equals true. It defaults to false, of course. And if you pass this option to the user settings in the ghc.next flake, then what it does is that it will bring the C toolchain necessary for building the GHC WASM backend into scope. And it will also override some environment variables to make the build the WASM backend instead of the native backend by default. So once you have the latest checkout of the master branch of the ghc.next repository, and you set this to true, and then you can start a Next shell and boot, and then configure GHC, and then you can just build the WASM backend. You don't need to pass any WASM specific flags with it. And after the build finishes, you can just use the binaries in the stage 1 directory to compile some Haskell source code to WebAssembly. And you can use WASM time to run it, because WASM time is also brought into scope by that flake setting. Now, if you're using a traditional glibc-based Linux distro like Fedora or Ubuntu, you don't use Nix, then it's fine. There is a repository, ghc-wasm.meta, which is hosted on the GitLab instance of the, So there are very detailed usage instructions in the README of ghc-wasm-meta, but if you want to seek for the installation instructions, it's getting started without Nix. You can just download a tarball or have a git checkout of this repository, and you run setup.sh, which should install everything in some directory in your home directory. You can also specify the skip GHC is 1, so that you can download less stuff, only the necessary things to build the GHC WASM backend itself. And after the installation completes, you can source the env file in this default installation directory, which will, again, bring into all the environment variables necessary for building the WASM backend. And when you run the configure step, do include the configure args environment variable, so that the necessary options are passed to configure to make it build the WASM backend. And the rest of the building step follows. If you are on other platforms, which is not x64 Linux, that's also fine. The WASI SDK toolchain that we use for building the GHC WASM backend has the binary artifacts available. If you are on like ARC64 Darwin or ARC64 Linux, we provide all of that, but you have to follow instructions in ghc-wasm.meta to get it set up. So I think this is pretty much about the building the GHC WASM backend, so we can probably just get going with the build. And finally, to the first slide of this actual talk. So David has already gave me a very good introduction, and there is not too much to say here. My GitHub and GitLab handle is @terrajack, and if you wonder about the origin of this name, we are not going to be conveying that in this talk, but we can chat a little bit about later. I am the current maintainer of the GHC WASM backend, and before that, I worked on an open source project called Asterius. So it is based on GHC, and it is sort of like GHC.js in the sense that it's an out-of-tree compiler, compiles Haskell to WebAssembly instead of JavaScript. And when working on Asterius, years, I gained all of the knowledge I needed about WebAssembly, about GHC and toolchains and compilation in general. And those experiences enabled me to implement the GHC WebAssembly backend as it is today. I joined Tweag in 2018 as a full-time Haskell developer, and that is also my first full-time job. And I have to say that I gotta thank the incredible patience of my employer, because not everyone gets to work on a project which spans multiple years and which makes some critical technical mistakes, as I will be demonstrating later. So yes. About this talk, first of all, this talk is not going to be a comprehensive usage guide of the GHC WebAssembly backend. There are some usage patterns, like how to use the GHC WebAssembly backend to compile some cabal packages, or how to pre-initialize a WebAssembly module so that you can run some Haskell computation and then snapshot the entire state of the memory into a new WebAssembly module. These kinds of advanced usage is conveyed in the GHC-WebAssembly-meta repository. So we are just going to be talking about some basic ways of using it. The assumption is that you are already a seasoned Haskeller, and thanks to talks from Ben, from other people, you already have some knowledge about the internals of GHC, but you don't know about WASM at all. So the first part of this talk is on the WASM side. We are going to be doing a quick dive into WASM, the specifications, and all you need to know about WASM to get started with hacking the GHC WASM backend. The part 2 is back to the GHC side. We are going to be going back to the GHC WebAssembly backend's internals, including the code generator and the runtime related things. And finally, if these two parts finished and there is still some time left, then I'm going to be doing some live codings to demonstrate what's the workflow for instance, adding the support for a new GHC primop into the GHC WebAssembly backend. So this is the prelude of this talk. Part 1 is a quick dive into WebAssembly. So what is the first impression of WebAssembly, actually? So it's something that enables you to compile once and run everywhere. Yeah, you have heard of that in other languages as well, but yeah. This has a totally new meaning. The simplest way of getting a WASM file and running it is in the command line. So as of here, I'm going to be showing you an example. I have a GHC checkout here, and I have a hello.hs. Well, it's actually not a hello world, not so simple as that. It's actually a Haskell module that makes use of GHC API. What it does is pretty simple. It reads all the standard input contents as Haskell source code, and then it uses GHC API, the parser part, to parse it into Haskell AST. And then it uses the GHC internal pretty printing functionality to reprint it to the standard output. So this single Haskell module is sort of a Haskell pretty printer, like Ormolu or things like that. It's pretty primitive. It doesn't handle the things like comments and such, but it's sufficient to demonstrate that we already achieve a lot with the current GHC WebAssembly backend. Now we are inside the next shell, which is backed by the GHC.next, and I have already completed a build in the GHC tree. So what we're going to be doing is so we are going to be calling the in-tree GHC to compile this to a single WASM module. Yeah, and of course, we already have a hello.wasm file in the directory here. And now we are going to be feeding this to the WASM file. And we can see that the program finished almost instantaneously. I actually cheated a little bit here because the hello.wasm file is a little bit large. Before optimization, it is like 10 megabytes or so. So when you call wasm time for the first time, it's going to be doing some fancy JIT optimizations, which is going to be taking a few seconds. But it has caching functionality. So the next time you use wasm time to run the same wasm executable, it's going to be pretty fast. So we can see that, yeah.
I had a question as well. That was this executable contains the GHC library and this program, and it's only 10 megabytes.
Yes, exactly.
Ah, That seems pretty small for the GHC library, actually. That's yeah, okay, wow, that's good. Okay.
This demonstrates my point of WASM is something that you can run in the command line. Yeah, this is an example. Another example is that, yeah, WebAssembly has web in its name, so of course it's going to be running in a browser. You have a question?
Is the WASM executable, is it a binary file or is it source, like the WASM source that looks like Lisp?
That's a very excellent question, which I am going to be demonstrating in the next slide, but it is a binary bytecode format. Yeah, okay. So my favorite browser example of the GHC WASM backend is the Ormolu Live. And of course, the other formatter, Formolu, they also have a similar version. So what we can do is just copy-paste some of the source code here. And then the formatter runs Ormolu on this Haskell source code instantaneously. So this is the proof that the GHC WASM backend is capable of running in the browser as well. Now, it can also run in edge computation in an edge server provided by Cloudflare or Fastly. So here is an example provided by Joachim Breitner. He made a simple example of using the GHC WASM backend to compile Haskell source code so that it's capable of running in Fastly servers and handle the incoming HTTP request. Yes, it doesn't do anything fancy like Haskell formatting, but this is another proof that it can run in the edge servers as well. And it can probably also run in your toaster. I haven't actually found a toaster example for this one, but the point is that a lot of the microcontrollers today are actually pretty juicy in terms of their computation capabilities. And there are WASM interpreters like WASM3. They are written in portable C, so that whenever the C compilers can target, the WASM files can get run. So it's quite likely that some brands of microcontrollers is capable of running WASM3 or some WASM interpreter like that. And we can run the WASM files produced by GHC on top of them. Yeah, so this is the sense of compile once, run everywhere for the GHC web backend. Despite its name, Andreas Rosberg has a very nice sentence I would like to repeat here. WebAssembly is neither web nor assembly. So it is not web because the original use case is motivated for highly efficient bytecode format that can run in all web browsers. But since then, the usage scope has expanded to the other cases as well. And it is not assembly because, yes, Zubin has just asked me a good question. And it is actually a compact bytecode format. It is binary encoded so that yeah, it is not assembly. But there do exist assembly syntax, as we will be demonstrating later. But why do we bother reinventing the wheel? Because, well, before WASM, we already have JavaScript that runs in all the browsers. We also have things like Java applets, Flash, or whatever, that a lot of the different bytecode formats that can run in a lot of environments. So why are people just not satisfied with the current solutions and come up with a new one? I am not going to be dumping a bunch of advertisements on the WebAssembly spec right now. Instead, I'm going to be diving into some technical details of WebAssembly. And then when we conclude the first part of this talk, I'm going to be providing my own answers to why people reinvent the wheel and come up with WebAssembly instead. So what is inside a .wasm file anyway? The simplest way to answer that question would be to check the official specification. Yeah, they have a very nice website which lays out everything you need to know about WebAssembly if you are a toolchain author which writes something that targets WebAssembly. Of course, we're not going to be going through every page of that official spec. And what we're going to be doing here is we are going to be trying to reverse engineer the .wasm file a little bit, disassemble it. The way to disassemble a WASM file is using a WebAssembly official project called WABIT. It's spelled this way, WebAssembly Binary Toolkit. So WABIT is also packaged by the Nix packages. So if you're a Nix user, you can simply bring it into scope using something like Nix shell, Nix packages, #WABIT. And yes, we have a shell which has all the tools necessary for disassembling a WASM file. hello.wasm 12 megabytes. Okay. So first thing we're going to do is that we are going to be using wasm2wat to compile the bytecode format into something that's human readable. Yes, exactly. Okay. WebAssembly textual format. They have now official textual format here. And oh, so it's 100 megabytes after expanding. Yep. We are not going to be scrolling through every line of it, but we are going to be going to some interesting places in the textual format. The next thing we are going to be doing is that there is another tool called wasm object dump, and this time we are going to be dumping only the headers of the hello.wasm, so we know what sections are inside this file. Oops. Redirect. Nice. So we can see that it's a binary file that's divided into different sections. So this is how a wasm file is organized. A wasm file breaks down into different sections, and each section has different semantics. Some are for type signatures, some for the imports, and some for the foreign reference tables and something like that. And the section order is not arbitrary. The wasm spec has carefully arranged the binary section orders in a way that enables single pass compilation to happen, so that when you are consuming the contents of later sections, you already have all the information you need in the previous sections. So the section orders are arranged in such a way. The term section may remind you to typical ELF executables as you may find in a Linux environment, but there are notable differences in the sections in a wasm file and sections in an ELF executable. So first of all, the most typical usage pattern of WebAssembly is static linking, which means that every .wasm file is self-contained. It contains all the necessary data segments and code it needs to support the functionality. So for instance, if you have dependencies on the libc standard library, or you have some dependencies against libfoo, then all of those are statically linked into your final .wasm file, as opposed to typical Linux executables, because most of the Linux executables, they dynamically refer to the libc in your distro. So this is the first notable difference here. And another notable difference between a wasm module and a ELF executable is that a wasm module needs to collect some extra metadata about its code in order to enable the compilation. So for instance, we can see that there is a type section in the beginning of a wasm module. And if we look at the disassembled textual format, we can see that this type section gathers a bunch of different distinct type signatures. So why on earth would I need to gather the type signatures of my already compiled functions into my final WebAssembly module? So we are going to be answering this question sometime later. Yeah, so this is what's inside of wasm.
Are those names generated by GHC? The function names? Are those function names? The numbers with the semicolons?
Yes. So in web, these numbers are auto-generated and they start from 0. So in WebAssembly, when you refer to a thing, like when you refer to a function in your current module, then you refer to them not by their names, but only by their indices. So this is the basic idea. Yeah. We have already seen one bizarre aspect of WebAssembly, which you have to collect a bunch of type information. So let's go a little bit into the WebAssembly type system. WebAssembly has a sound type system. It has typing rules with a lot of Greek letters, as you would expect in those type theory papers. And it has complete verified implementation using the Isobel language. But why do we need a type system for such a low-level intermediate representation? We can just answer that question later, but let's look at what kind of types is supported by WebAssembly. The most elementary type supported by WebAssembly breaks down to the value types, or I would like to say atoms. They are 32 and 64-bit variants of integers and floating points. And I32 is also used as booleans and pointers. So value types are pretty self-explanatory here.
Was that an exhaustive list of the atom types, or like are strings like sort of?
That's a good question. Actually, there are more than that because, for instance, there are SIMD vector types, and there are also reference types which refer to the opaque reference things in the host environment. But for simplicity, we are going to be just covering these basic types of value types. Yeah. And then, by composing the simple atom types, we can form a vector of value types, which is result types. So result types can be used to describe what is returned from a function or what is returned from a block, things like that. And we have function types, some value types, and then produces some value types. And this function types, despite its name, is actually also used to type the blocks in the WebAssembly. The basic idea is that all the computation in WebAssembly happens on a value stack. If I want to say 2 plus 3, then that will be something like i32.const2, which pushes the constant 2 onto the stack, and then followed by i32.const3, which pushes the constant 3 onto the stack, and then a single opcode, i32.add, which consumes the top of the stack, the 2 elements, and then pushes something to the value stack instead. This is how computation is typically organized in WASM. So in some sense, it is a stack-based machine. Now, if there is not enough values on the value stack, then it's going to be either a compile time error or a runtime error. Most of the time it's compile time error because there are typing rules for every single opcodes in WebAssembly, and there is a compile time validation which guarantees that these typing rules are not going to be violated at runtime. And there are edge cases like indirect calls which require you to do dynamic type checks at runtime, and we are going to be going through those things later.
So I guess, I mean, just to clarify, you mean there's a type checker,
yes,
but it's not exhaustive, statically exhaustive. It won't catch every unsoundness, but those the necessary type checking will be moved to runtime to ensure soundness.
Yes.
So that's the point. Okay, yeah.
Yeah. Now, what is inside a WebAssembly function? So when we talk about WebAssembly function, first, we want to talk about how do we invoke these functions? How do function calls occur? So when you are compiling a function towards RISC-V or those typical ISAs, then you have to convey to a calling convention. Like you have to push your arguments either in some global registers or spill them on the stack, and then you jump to the code of the function entry, which is, again, not the case in WebAssembly, because in WebAssembly, every single function is typed. You can specify the parameters and return values of that function. And then you just use a single call opcode, and then the arguments and return values are handled. And of course, they are type checked at compile time for the static calls. But for the dynamic calls, like call indirect, then the WebAssembly specification says you have to perform a runtime check. And if you intend to call a WebAssembly function which has type A, but you're passing the arguments of type B, then it's going to be panicking. Yeah, so this is how it guarantees the soundness of function calls. Another notable property is that in most of the architectures, the call stack is something that you can see in memory. So for instance, in C, there is set jump and call jump, which allows you to somehow do the non-local control flow transfers. This is possible because the code of set jump and long jump is able to inspect your current C call stack as a memory region, and it's able to unwind that stack as necessary. And again, this is not the case in WebAssembly because the function call stack, which in WebAssembly terms is the control stack, it's completely hidden from all of the WebAssembly code. There is absolutely no way to inspect the control stack. There is no way for the WebAssembly code to manipulate this stack for your own purpose. It's completely opaque. So this is a technical choice for the both the efficiency of the compilation and for the safety of your code, because smashing your stack is, of course, the most typical source of attack vectors here. Yeah, and one of the things I slightly dislike about WebAssembly is that tail calls, it seems explicit tail calls, the kind of tail calls that you have to guarantee it doesn't grow the control stack, otherwise compilation fails. There is that experimental WebAssembly proposal about tail calls yet, but it's not widely implemented in all of the runtimes.
I have a question from Eduardo. He says, I remember seeing repetition of function types in VS Code. The only difference was the value types. Does this mean we don't have polymorphism?
Polymorphism, let's see, only a few of the WebAssembly opcodes are actually polymorphic in their type signature. So for instance, if you use the unreachable opcode, and then the unreachable opcode just abandons the runtime state, and it's irrelevant in what types are on the value stack. And there are other opcodes as well that is stack polymorphic. I don't know if this answers the question.
Now I'm interpreting his question, but I think he was asking about the function signatures that showed up at the top of the WebAssembly header.
Can you have a polymorphic WebAssembly function that doesn't do anything with, okay, the ML style polymorphism. Yeah. Nope. Okay. Nope, that is not, that is not supported in WebAssembly. Yeah, all right. So we were talking about tail calls in WebAssembly, and there is already an experimental proposal, but only V8 implements it so far. So we have to wait a little bit until we officially enable it in the GHC WebAssembly backend for using it to lower the CMM function calls. And I said that WebAssembly is a stack machine, but it's not just a stack machine. So you don't need to force all of your operands on the value stack. You can have a construct called WebAssembly locals. So this is another nice thing about WebAssembly is that you can forget about a fixed set of machine-generated registers, and you don't need to do anything for register allocation. When you are compiling a CMM function or whatever low-level function to WebAssembly, you can imagine that you have that infinite supply of these tiny little WebAssembly local registers that you can just use. And then it's up to the WebAssembly engine to efficiently use the machine registers to represent these locals. So you don't need to do any sort of register allocation when you're lowering to WebAssembly. And then locals are only scoped inside a single WebAssembly function, but sometimes you want to share some values across multiple WebAssembly functions, in which WebAssembly has a construct called globals. So you can use WebAssembly globals to represent things like R1 in CMM or the stack pointer or heap pointers, things like that. So you can use the locals and globals for these purposes. And finally, WebAssembly has a linear memory space, of course. Ben has already described in his talk that occasionally GHC needs to emit code that spills the arguments on the stack. And this is the same thing that we are doing here. The linear memory is used to represent the heap memory that is used by the Haskell runtime system. So yeah, you can use linear memory for this purpose.
If you don't mind, so the globals mentioned there makes me think, is there a concurrency story here? Like, is this a single-threaded machine? Like, is there any notion
yes,
of...
we are only going to be talking about the single-threaded variant of the WebAssembly, which precludes all your concurrency issues here.
Okay.
Yeah, there do exist the threads and atomics proposal of WebAssembly, and it's implemented, but we are not implemented that in GHC WebAssembly backend yet. So
sure. Okay.
Yeah, that's omitted from the talk.
Simplifies things.
So in a lot of the intermediate representations that are low level, including CMM, there is a clear distinction between expressions and statements. But in WebAssembly, all of the expressions and statements are actually just special cases of WebAssembly opcodes. So you can think of expressions in CMM as some WebAssembly opcodes which eventually just pushes a single value onto the value stack. Yeah, and the statements are just 0 to 0 functions. You can think of them that way, that may consume something on the WebAssembly, that if it consumes something on the WASM value stack, then it's going to be pushing the same amount of the values onto the stack, so that in the end, it doesn't actually modify the shape of the stack in any way. So yeah, expressions and statements are just special cases of the WASM opcodes. And Now, we have talked about control flow, which is inter-function, but we can talk a little bit about the control flow inside a WASM function. So the easiest way to do that would be using the compiler explorer, the Godbolt website. I like to use it to demonstrate simple cases for the ISAs like WebAssembly. So you can open the compiler explorer here, choose the C language, and then choose the compiler is a WebAssembly CLang trunk. I'm adding an optimization flag OZ here, which stands for enable every single CLang optimization that is guaranteed to reduce the function size so that you can get somehow compact output here. Here is a really simple example of a Fibonacci function, which is recursive, and it doesn't do any fancy optimizations. But the generated code, it already contains some of the interesting cases that we are going to be covering in this talk. So yeah, we can see that fib compiles down to the textual format like this. We have the constants, and we also have local.set, local.get, which is, well, we know, setting and getting the local values in the current WebAssembly function. And then it comes to the control flow within WebAssembly functions. There are two basic building blocks within the WebAssembly control flow. One is block, and the other is loop. We can think of blocks and loops as the starting point of a special scope. And then inside the scopes, which of course can be nested, you can use the branch instructions, which jumps to either the end of a block or jumps to the beginning of a loop. So, and the branch instructions, they have to take that indice, and that indice represents the current nesting level of your blocks. So this is how the local control flow is represented.
So block is the beginning of a block and loop is the end? Is that?
Nope.
Okay,
both
good.
the block and the loop keywords, they are starting a new scope. And then you can see at the end of the scope, there is always end loop and end block. So you can think of them as the left curly braces and right curly braces. Yeah.
Okay.
Of a scope. Yeah. And one tricky part about this local control flow is that there is no arbitrary go-tos here. So the control flow is completely structured. If you want to use the branch instruction to jump to somewhere, then the only place that you can jump to is either the beginning of the end of a block or a loop scope. And you have to be already inside that scope to be able to reference that scope by its ID. So it's completely structured control flow. This will cause you some difficulties when you try to lower a control flow graph, which may contain arbitrary go-tos at the end of the basic block. So yeah, we are going to be introducing that later.
Just to make that concrete, could you go back a slide maybe? And just very quickly, yeah, that's right. The branch, I don't know, line 9 right there. What does that index refer to? Which of the block or the loop?
It refers to the block, not loop. So the basic idea here is that when you want to refer to a scope that you are already captured in, the indices start from 0 and goes upwards, and it starts within the innermost scope, not the outermost. So loop is 0, and you can refer to the block as 1.
Okay.
Yeah.
Thank you.
Sort of like the bridging indices in lambda calculus.
Right.
Yeah. So yeah, so this is inside a WASM function. You can do computations using locals, globals, linear memory, and you can do the fancy transfer flows. And next thing we are going to be talking about is the WebAssembly linear memory. Yeah, there are some simple aspects about the linear memory. So first of all, the linear memory is a 0 initialized buffer, and there is no such thing as uninitialized memory in some sense, yeah, in WebAssembly. So, and when you are compiling a WASM module that makes use of linear memory, you can also optionally put some data segments that is used to pre-initialize some parts of that linear memory, and we are going to be using it in the GHC WASM backend. Yeah, so the linear memory is such a buffer. And another characteristic of the WebAssembly linear memory is that all of the memory operations, the loads and stores, the WebAssembly specification says the runtime must bound check them. So this precludes the possibility of the buffer overflow. Yeah, in WebAssembly. The page sizes in WebAssembly linear memory is 64 kilobytes, which is a lot larger than the typical 4K limit in Linux. And all of the memory growth is possible at runtime. You can query the current size of the linear memory in the units of pages, and you can grow them by whatever pages you want, as long as you're not running around the 4 gigabytes limit of the WASM32.
Beyond being the unit of allocation or reservation, what does the page notion have any other meaning here, or?
Nope.
Okay.
Nope, it doesn't.
It's just a unit.
Yeah, it's just a unit. Yeah. And regardless of whatever runtime you are going to be running your WASM32 modules, the linear memory space is a simple 32-bit little endian memory space, so that even if you're running WebAssembly on a big endian machine, then all of the WebAssembly memory loads and stores are not affected by the endianness of your host architecture. So this is one thing that makes WASM portable. Now, another slightly bizarre characteristic of the WASM linear memory is that it's allowed to do misaligned access of the I64 and I32 values and things like that. Things like this. But we all know that misalignment of the memory loads and stores is typically a very bad pattern when you are compiling code. And it may generate a sick bus in some of the architectures. And the way WebAssembly mitigates this problem is that all of the memory load and store opcodes in WebAssembly, they may be optionally decorated with alignment info. So this allows you to say, I want to load a I64 value, but this value only has the alignment of I32 bytes. So the WebAssembly runtime can probably lower that WebAssembly opcode into 2 adjacent memory loads from I32 values to prevent this kind of misaligned access. And the GHC CMM actually has this alignment info in the CMM memory loads and stores, and we are making use of that. And there also exist some special opcodes, bulk memory opcodes, which allows you to inline the memcopy operations as a single WebAssembly opcode instead of calling the memcopy function in WebAssembly. So bulk memory opcodes are a potential for copying the large buffers in WebAssembly in a very efficient manner, because they don't actually go through the WebAssembly implementation of memcopy, and instead they just delegate to a host memcopy operation here. Now, the linear memory is simple compared to the Linux virtual memory in a sense that there is no virtual address space, so there are no holes in the available linear memory address space. And Ben has talked about memory pages, and in WebAssembly, there is no page-level permissions. You cannot make read-only WebAssembly memory pages, things like that. And you cannot implement mmap in WebAssembly. So these characteristics makes it a little bit harder to actually make the GHC storage manager work on WebAssembly, which we are going to be describing a little bit later. Now, another final surprise for the WASM linear memory is that 0 is a valid address. You can actually read something from the 0 address. And we know that in compilers, usually the null constant is desugared to 0. So the way that we mitigate that problem is that the WebAssembly linker, usually it lays off the data segments in some place which is indexed off 0, so that you have a few bytes in the beginning of the linear memory, which is not used by anything. So this is how this null memory problem is handled in WebAssembly. Now, all of the memory loads and stores, if they are happening in a single-threaded runtime, you don't need to care about things like sequential or consistent or something like that. But it's actually possible to run multi-threaded WebAssembly applications which share the same linear memory space. And then you are going to be having some special memory opcodes which does the atomic loads and stores. And you can use them actually to implement something stronger, like implementing futexes or spin locks on the linear memory space, but we are not using those extensions. So I'm just describing that it's possible to do that in WebAssembly, but it's not used by us, and we are not going to be going down that rabbit hole. Now, besides the WebAssembly linear memory, which is only used to contain the data part, we also need to talk about the WebAssembly table, which is referred to code. So in WASM, unlike x86 or other architectures, the data and the code are strictly separated. We already know that you cannot see or manipulate your function call stack, but it's actually a little bit stricter than that. The WebAssembly function code, they are completely hidden. You cannot use some special opcodes to read the function code as binary data and manipulate them. So you cannot read or write the function code in WebAssembly in any of the address spaces. So this brings us a challenge because you may still want to refer to some of the WebAssembly functions so that it's able to put these function addresses in some data structures like info table or whatsoever. And you want to do indirect calls based on these function pointers. So the way WebAssembly enables these kinds of indirect calls is that in addition to the linear memory, it also has a data structure called the WebAssembly table. Is a vector of opaque references that may reference WebAssembly functions themselves, or they may also reference some host resources. Like if you are using the browser as the WebAssembly host, then it may refer to the JavaScript values as well.
Can you allocate these things at runtime, or are they statically known?
Most of they can be statically known as elements in the table, but you can also manipulate these things at runtime.
Okay, and they're mutable.
Yeah.
Okay, yeah, that makes sense.
Yeah. And another characteristic is that the WASM table is a resource which you can use to do the indirect calls across WebAssembly functions, but not every WebAssembly function needs to end up in the table. Only if the compiler determines that the addressing of a certain function has appeared in the source code, you need the function address. Only by then it will put the function in the WASM table, and most of the functions in WebAssembly aren't actually going to be ending up in the table. The call indirect opcode in WebAssembly, they don't take the function indices in the function namespace. They only take the table indices. And this has a nice property in that it makes it possible to do some post-link optimizations. For instance, if you take a linked WebAssembly module and then you perform some optimizations, then later it may be possible that some of the functions, they do not appear in the table. So you can be absolutely sure that they aren't call indirected. And they also are not referred to by their function indices. Nobody is calling them in directly. So it makes it possible to strip these dead functions after the linking. So this is one benefit of using the table instead of using the function indices for referencing the WebAssembly functions. Now, WebAssembly itself is just a computation spec. There is a question there.
Doesn't this make call indirect very unpredictable, since the programmer doesn't know the table index, just the function index?
I don't think so, because by the time you already link a WebAssembly module, all of the table indices already know.
Yeah, but when I, as the programmer, use, or is call indirect not meant to be used directly by programmers?
If you are going to be using function pointers in C, or if you are writing Haskell, then of course you're already using call indirect. So, okay, I get your question now. In terms of separate compilation, if I want to refer to some function in the current C file or another file, do I have to worry about the linker messing these indices around? Is it? It's not a question, because actually when you write a call indirect, you don't use the table indices. In your source code, you always refer to things by symbols, and symbols are strings. They are always stables, and it's the linker's responsibility to change these symbols into the final integers in either the function space or the table space.
Oh, I see. Yeah, thank you.
Yeah, nice. So another thing we are going to be covering here is the imports and exports, because WebAssembly itself is just a computation spec, and merely performing some arithmetic in the and computation is not going to be useful. You want to read and write your file system. You want to work with sockets or fire missiles or something like that. In order to do these side effects in WebAssembly, all of the side effects has to be provided to the WebAssembly module as imports. Things that can be imported and exported include the WASM functions and also the host functions. And the table and memory can be imported and exported as well. And this permits the host function to manipulate the WebAssembly linear memory as well. So what kind of imports we want to provide to our WASM modules, and specifically the modules produced by GHC? So there is another concept that we need to go into here, the WebAssembly system interface. What does the WebAssembly system interface look like? We can go to this textual format and search a little bit for import. And what do these imports look like? Every single import in WebAssembly, they have two components. One component is which namespace it lives in. So you can have different imports with different namespaces. All of the WASI imports currently, they are in the WASI snapshot preview 1. And then we have the names of these different imports in the same namespace. And we can see here, there are imports that allow you to work with the function art.
These imports, didn't you say that these WASM files are self-contained? That is, they don't import anything. They just hash include everything they need.
Yes.
So how can it import anything if it's self-contained?
So self-contained is only in the sense that it doesn't use dynamically linked libraries, but all of the side effects that it's going to be causing, it has to import from the host environment.
So it's not quite, it hasn't got quite all of its dependencies.
Yes.
It
yes.
explicitly has a bunch of dependencies on this mysterious thing called the host environment.
Yes, exactly.
Okay.
Yeah, that's the point.
But and the host environment wouldn't include things like libc, but it might include things like Linux. Is that the idea?
No, it doesn't make use of the Linux libc. So the point is that the libc of WebAssembly may make use of these imports transitively. Yeah. So the libc code is still statically linked into the WASM module, but if they want to perform any of the side effects, they have to call one of these things. So they can be sort of the syscalls, but not for Linux, but just for WebAssembly.
Out of curiosity, who would provide these WASI functions typically? Is this the runtime, I guess?
Yes, the WebAssembly runtime.
Yeah, okay.
I assume you can also make your own WASM modules and load them somehow similar to dynamic linking. Is that possible? Like explicitly using dynamic linking? Something similar to it.
You mean, is it possible to do dynamic linking in WASM, like dynamically
any kind of dynamically loading modules or?
Yes,
Okay.
that's possible. In mscripting, you have the dynamically linked libraries, but we're not using that yet. Right, so the idea of WebAssembly system interface is that in addition to the WebAssembly core specifications, you need something that allow you to do things like command line arguments and system clocks and file systems and all of that. So you can think of it as a very portable subset of POSIX, but it's not quite POSIX. And typically, you don't write calls to these WASI imports in your user code. You just use of the libc functions. And these libc functions are going to be calling these WASI interfaces sometime, yeah.
And just one more question, or two more, I guess. Can you actually go back to the imports that we were looking at earlier? And if you scroll to the right there, they have types as well, right?
Yes, exactly.
And those refer to the types in the type
yes,
section. I see.
Yes, exactly.
Yeah, okay.
This is a question from Gergo. Would handwritten JavaScript code, for example, to interact with the DOM, show up as imports in this sense?
Yes, you have to do that with imports as well.
And I guess there's some sort of mapping between the C-type system and the WASI type or the WASM type system?
Yes, there is a C API which says which C types are going to be represented by which WASM types. WASI is an addition to the WebAssembly spec that says which syscalls you can use. And we target WebAssembly 32-WASI. We don't use mscripton, and we don't want to pay for JavaScript when we don't use it. All right, yeah. So they can coexist with other JavaScript imports as well. All right, everyone. So we've just covered imports, exports, and the WASI specifications in our previous talk. And now, if some of you have already known the word Asterius, that's the experimental compiler that I worked on a few years ago, which also targets WebAssembly from Haskell. And this slide contains the critical difference between the GHC WebAssembly backend as it is today and the Asterius project that I worked a few years ago. So suppose you want to write a compiler project that targets WebAssembly, this shiny new thing buzzword. And what are you going to do? First of all, you're going to be reading the WebAssembly specification. And then you know that there are these different kinds of opcodes, different sections, these kind of things. And now you are going to be writing or using an existing library, be it in Haskell or any other language, that represents the WebAssembly abstract syntax tree in memory. And once you have such an AST representation of WebAssembly, then you can just omit a WebAssembly module from your low-level intermediate representation, right? Is that everything going to be working out of the box? Sadly, the answer is nope, because we are missing a big piece in this whole jigsaw puzzle, linking. We have to admit different object files, and these different objects files are going to be containing entities, data sections, functions, things like these that reference each other by their symbols. And this is something that has been missing from the official WebAssembly specification. And I wish I had known this critical thing a few years ago. Now, all of the knowledge that we have accumulated in the previous slides of WebAssembly, it doesn't allow us to generate a special piece of WebAssembly module that contain symbols instead of the table indices or the memory addresses, contain just symbols that can refer to external things. Yeah, and the point is that if you're writing a WebAssembly compiler and you cannot link with C, then you are very likely doing it wrong. So first of all, not being able to link with C, the C libraries, means that you have to reinvent the wheels in some places. Like for instance, if you want to do heap allocations and malloc and these kind of things, then chances are you are not going to be coming up with a more efficient implementation than what it is in the WASI-libc today. So you have to reinvent these wheels in many places. And Asterius started as such a project that it takes CMM as a low-level intermediate representations as the starting point for compiling to WebAssembly. Then what it does is pretty simple. It converts CMM to an in-memory representation of the WebAssembly IR, which is, of course, a Haskell library. And then we wrote bindings for the binarian C++ library. And then at link time, we just deserialize these Haskell data structures from the object files, and then we perform our own custom linking logic. We gather a big WebAssembly module in memory, and then we are going to be just calling the binarian library to serialize that as an actual WebAssembly module. And the missing piece from this linker story is that it's unable to link with C. Now, Asterius has proven that if you are unable to reuse any of the existing C bits in the GHC RTS, then it is very challenging, I would not say impossible, to reinvent the wheel of Haskell RTS and come up with something that's compatible with CMM as it is today and is also efficient in terms of garbage collection and all of that. So how are we going to be emitting a special WebAssembly object file which can be linked with other things, can refer to the other entities in other object files? Now, there is such a thing called the linking convention in addition to the official WebAssembly specification. I can take you a brief look at what this tool convention looks like. So it's a GitHub repository in the official WebAssembly namespace. There is an object file linking document which specifies that some custom sections in a WebAssembly module, they can contain the things like symbol tables or relocation entries. So they can specify that these function indices, these table indices, these numbers aren't actually absolute indices into their namespaces. Instead, they are referring to some symbol which may or may not be defined in the current module. They can be defined elsewhere. And the WebAssembly linker is in charge of, at link time, collecting these things, stripping the unneeded entities, and also rewriting these integers to the correct places in the WebAssembly table or linear memory. So this is what the linking convention looks like. And yeah, so a linkable object is just a special .wasm file that contains these relocation entries. And your compiler, you should be emitting these object files with these relocation sections. But how? Because there is no existing library in Haskell or in other languages that is aware of this linking convention. Well, LLVM, of course, it does, but the LLVM library is pretty hard to reuse in a compiler project. So the best way to do it is not to just attempt to omit these relocation sections in your binaries itself, because meddling with those binary indices is very likely to go wrong with things like with a lot of issues. So actually, apart from the .wat, the WebAssembly textual format, there also exists a standalone format, the WebAssembly assembly format, which is just like assembly for the x86 or other architectures that enables you to emit a WebAssembly module that can be linked against other modules. And you can refer to other things, other entities by their symbols. So you can emit this textual assembly format and have CLang to compile it into an actual object. We are not going to be going into the details of this textual assembly format here, but I want to give you an idea of how it actually looks like. So basic assembly. In the LLVM project tree, there is a very big example, basic assembly.s, that kind of covers all the features that's going to be present in this assembly file. So just like assembly sources for other architectures, you have these directives to provide additional metadata. For instance, if you refer to a function symbol instead of a data symbol, then you absolutely have to provide the correct function type signature here. Otherwise, at link time, at runtime, you are going to be getting validation errors. And in these functions, the code in each different functions, the code format is kind of like the code format as we already see in the WebAssembly textual format. So and you can refer to things by their symbols. And other than the code and the function signatures, you can also use special directives to put some data sections in this object file, and you can even specify some metadata such as the alignment for each data sections like these. So this textual format compared to the linking convention, it's not actually a very well documented thing. So you have to dive into the LLVM implementation a little bit to gather all the aspects to implement it, but it's actually pretty straightforward. So this is what I wish I knew a few years ago. You shouldn't be relying on a third-party WebAssembly library and just emit a whole standalone WebAssembly module. Instead, you should be emitting objects that can be linked with the C world, and being able to interact with the C world is a critical thing towards success. So the conclusion of part 1 is, now we go back to answer the question we have at the beginning, why we reinvent the wheel and have another bytecode format. So first of all, compared to JavaScript and Java applets and other garbage collection languages, WASM is incredibly low level and easy to lower to an actual hardware architecture. So it is efficient and it is portable. It allows you to forget some machine-specific details like how to do register allocations, how many registers I have in my current CPUs. The semantics of a WebAssembly module is guaranteed to be the same regardless of your host architecture. So this is the one benefit of WebAssembly. Another benefit of WebAssembly is that it puts safety first. So it has the type system for guaranteeing that these opcodes execute in the correct manner. And the most important thing is that it has the security through capabilities thing. If you want to perform any side effects, you want to read or write a file, or even if you just want to query the current timestamp, all of these cannot be provided in the WebAssembly spec. You have to provide it as a standalone import. And whatever import you provide to your WebAssembly module guarantees that whatever side effect that it can perform. And last thing is that WebAssembly is driven by working groups that has participants from multiple vendors from different big companies. So the governance model is pretty open. And it is also an evolving standard. Apart from the minimal viable product of WebAssembly, which is already out a few years ago, there are also different proposals of WebAssembly that adds different opcodes to WebAssembly for new functionality. And these proposals, some of them has already been widely adopted, and the GHC WASM backend is already making use of some of them. So yeah, WebAssembly is also a moving target. Now, compared to different ISAs like RISC-V or whatsoever, there are aspects that make it easier to target WebAssembly. Yeah, we don't need to worry about the ABIs for argument and result passing. We don't need to consider register allocation and things of this. And a very nice property of WebAssembly is that it has an excellent tool called WASM-opt. So the idea of WASM-opt is that it performs extensive people optimization on already linked WebAssembly module, so that you don't need in your compiler's code generator to spend a ton of effort to generate already optimal code, because a lot of these optimization passes can be done more efficiently by the WASM-opt executable. So the GHC WASM backend is just a very straightforward translation from CMM to WASM, whatever possible. And a lot of the optimizations is guaranteed by either the platform-independent optimizations passes on the CMM, or we just leave it to WASM-opt. And WASM-opt is traditionally able to shrink about 40 to 50% of the already linked Haskell modules. So yeah, while maintaining the performance characteristics. So it's pretty amazing in that aspect. There are also some properties of WASM which makes it slightly harder to target compared to the other ISAs. So first of all, because the control flow has to be strictly structured, you cannot have arbitrary go-tos in the WebAssembly. So if you want to lower control flow graphs with these kinds of go-tos, then you have to implement a special relooper algorithm. Yeah, and dynamically loading modules in WebAssembly at runtime just in time. So first of all, the WebAssembly, because of the strict distinction between code and data in WebAssembly, using pure WebAssembly without any help from the host to do the JIT compilation is not possible. And even with the help of the host, you have some special functionalities to do the symbol relocations and the code linking at the runtime. Then it's still a pretty tricky thing to implement JIT and dynamic code loading. So yeah, as of now, the GHC RTS linker and the GHCI is not properly implemented in the GHC WASM backend first. So, but it will be implemented at some point in the future. And also another property is not about WASM spec, it's about WASI. WASI is a strict subset of the POSIX features. It's pretty limited. So if you are going to be porting some large existing code bases in C or C++ to WASM32 WASI target, then chances are the compilation is not going to be succeeding out of the box, and you have to patch these code bases to get rid of certain features like POSIX threads, signals, kinds of things like that. So yeah, it's not trivial to port existing code bases to WASI. And debugging a WebAssembly, the debugging story has kind of improved in the last few years, but the situation is not satisfactory yet. The most efficient way of getting things work in WebAssembly is getting them work already in our 32-bit targets like i32, i386, and then fingers crossed that it works in WASM32. And most of the cases, it actually works in WASM32. So yeah, debugging is still harder than it should be. So these parts about WebAssembly spec has already been covered, and let's go into the GHC WASM backend. But what is the GHC WASM backend anyway? So GHC, in addition to be built as a native compiler that targets the same architecture, it can be built as a cross-compiler. When you configure the GHC build, you just pass the host and the target, and then provided that you have the toolchain available for compiling C code for your target architecture, then it can be built as a cross-compiler. So across GHC has three components. One is the cross-C toolchain, especially including the C standard libraries that's already in the form of target libraries. And then you need to build a global package database which contains code that is in the target architecture. And finally, the cross-GHC. So the third part can be improved a little bit. Rodrigo is working on making GHC a runtime retargetable compiler, so you don't have to always rebuild GHC whenever you are targeting a new architecture, but that is not going to be happening in the short term. So first of all, to get the GHC WASM backend working, we need a WASI SDK, which is a packaged version of CLang and all those LVM tools. And we also patch the libc for WASI target for some reasons described later. And apart from the C toolchain, we also need work in the RTS, in the standard libraries like base and Unix, and also a little bit of work in the build system, the Hadrian and all the autocomp scripts to make them fit together and work for the GHC WebAssembly backend. Yeah, not everything in the RTS work out of the box because, well, of course, WASI is not POSIX, so we need special logic in certain cases. And apart from the work in RTS and standard libraries is the code generator, which is capable of consuming the CMM in memory and generating the WASM object files, which can be linked against the C world. And currently, I haven't really tested the LVM code gen of GHC, and we don't know if it works out of the box. But the unregisterized code generator and the native code generator already works pretty well for WASM 32, and yeah. And finally, there has to be some work in the GHC test suite because the GHC test suite used to assume that every executable produced by GHC can be run as a native executable, which is apparently not the case for WASM 32. So we need a bit of work in the test suite to make it recognize a so-called cross emulator. The emulator can be used to run your WASM modules or the executables of other architectures and translating all the syscalls. So now let's get to the RTS storage manager part. And Ben has already did a very wonderful introduction of the RTS storage manager. And most parts of the RTS storage manager actually work out of the box for WASM 32, except the n-block allocator. So first of all, I want to emphasize a point is that we reuse the existing RTS storage manager for garbage collection, and the heap entirely lives in the linear memory. There used to be, some of you may have heard of the term WebAssembly garbage collection. There is an ongoing proposal in the WebAssembly world that enables the WASM world to reuse the existing garbage collection functionalities in the host, like the JavaScript engine's garbage collection. So to use these opaque host objects to represent the WASM objects as well. So we looked a little bit into the possibility of using that to represent the Haskell programs, but in the end, it turned out to be a very huge engineering effort. And apart from that, the real challenge is that the design of a garbage collector is much tied to the capabilities which is required by the mutator. And GHC does a lot of weird optimizations regarding garbage collection. For instance, you have to short out the selector thunks. Selector thunks is already described by Ben's talk, and you also have to deal with things like black holing and rewriting the indirects, and a lot of these functionalities is impossible to implement if we are using the WebAssembly garbage collection. So in the end, we thought that the lowest effort is the best effort. We just cross-compile the existing RTS and make use of the existing garbage collector. Yeah. So a quick recap of the structure of the RTS storage manager. The highest level of the RTS heap is different heap objects closures. And these closures are also always contained in a data structure called the RTS blocks. And there is a dedicated block allocator in the RTS to manage the 4K sized blocks. And all of the blocks and their block descriptors are contained within 1 megabyte size of megablocks. And the megablock allocator interfaces with the operating system directly, so it may use mmap or other syscalls to grab these m blocks and then make them available for the upper levels of Haskell heaps. So yeah, apart from the m-block allocator, the rest of the heap allocation in Haskell is architecture independent. But recap that the WebAssembly linear memory is actually a very simple linear buffer. We don't have page-level permissions. We don't have holes in the address space. And we also have no mmap. So we can only query the current WASM memory size in terms of pages, and we can grow them by certain pages. So how are we going to be porting the megablock allocator onto the top of the WASM linear memory? Now, the first approach, which I've tried for some time, is in the newer versions of libc, there is a function called aligned alloc, which allows you to allocate large buffers from the C heap. So what we're going to be doing is calling this libc function to allocate buffers which are sized in multiple megabytes, and it is aligned to 1 megabyte boundary, which is a hard requirement for the mblock allocator. So we can call this to grab the memory from the C heap, and then we can call free to free these buffers when we need to return them to the libc heap. But that comes with a challenge, because the mblock allocator, it doesn't always immediately return the unused megablocks to the OS kernel. Instead, it maintains the internal free lists of these different megablocks, and it may join the adjacent mblocks together in the internal free list if their addressed ranges are adjacent, which brings us a problem, because if we do the mblock allocations multiple times and we end up with different mblocks, and then they are joined together in the internal free list, and then we call free, then we are only freeing once the starting block of the mblock group, and the rest of the blocks, they are completely forgotten, and this is a source of space leaks. Or of course, we can maintain additional metadata in the block descriptors so that to force, whenever we call an aligned alloc into the libc, we also always call the free on the returned megablock allocators, but that is paying for something which is not needed on other architectures. And we want to minimize the penalty for the other existing targets for GHC whenever possible. And another problem is that it wastes about at least 50% of the linear memory because of the implementation detail of the libc allocator. You see, most of the libc allocators are implemented in such a way that it maintains a few words before the immediately returned pointer. These words are used to store some metadata about the allocated buffer, like how large is it, or which block group it is belonging to. So this is not a problem for small allocations, but it becomes a problem when the typical allocation pattern of your program is just these 1 mega-sized byte mega blocks. So when you allocate a big mega block, then you need a few bytes before this mega block address to do this bookkeeping about these metadata. And this, in turn, makes it impossible to allocate another mega block, which is immediately adjacent to the current mega block. So you are going to be wasting a lot of the linear memory, which is not possible to be used by the Haskell heap. So this turns out to be a problematic approach. And the current approach we have is we have a osmem.c, which is dedicated for the WASM32 target, and it directly grows the linear memory by 1 megabyte sized. So in this way, we can make sure that most of the linear memory can actually be dedicated for the use of Haskell heap. Now, this approach has its own limitations. We have to patch the existing libc allocator in the WASI-libc to make it better suited for the allocation patterns of the RTS storage manager. And also, another problem is that when we exit the Haskell RTS and return all the resources to the C runtime, it's impossible to return the Haskell heap space to the C heap. Well, this is not going to be a problem for most of the Haskell applications here, because well, most of the linear memory is going to be dedicated to the Haskell heap anyway, and when the Haskell RTS exits, it's the time when the entire program exits. So, well, it's not going to be a problem for typical use cases. But if you want to compile a Haskell app as a static library and then embed that library into a bigger C or C++ project, then it will become a problem. But I haven't heard of these kinds of use cases yet. So, yeah. Any questions so far?
Linear memory. My understanding was it was scoped somehow, like it was per module or every. Is that not the case, or is it per program? Is there one linear address space per program, or is there?
Yes, it's per program.
Okay. My mistake then. I see.
Yeah.
Because you said you could export linear memory as well.
So when we talk about export linear memory, we are not just exporting a region of it. Instead, we are exporting the memory as a whole. Yeah.
Okay.
This is the only kind of memory is that.
Okay, so there you can't have like multiple linear heaps, which one you could use for C allocations, one you could use for Haskell allocations.
Actually, it is the case that there are two heaps that are coexisting in the same address space. There is the libc heap, which is managed by libc, and there is the Haskell heap, which is its space is obtained by directly growing the memory. So the libc allocator in the WASI libc, it is capable of detecting that since the last time I called SBRK, the heap space has been grown by someone else. It is able to take that into
But they
account.
coexist in the same address space.
Yeah,
Okay, that
they
was my
can
question.
coexist.
Really. Yeah, thank you.
Yeah, so this part is about the RTS storage manager. And yeah, so in the future, this may become a little bit tricky when we want to have the opaque host resources on the Haskell heap. For instance, we are going to be adding first-class interoperability with the JavaScript world. That requires us to have JavaScript values as garbage collected Haskell values on the heap. And how are we going to do that? Well, it should be possible with some tricks, like we have to manage the JS values on the Haskell heap by not storing the actual JavaScript values in the linear memory, because of course that's not impossible. We are just going to be storing the handles to the actual resources. These handles can be just integers on the Haskell heap. And we have to add some hooks to the Haskell garbage collector so that it's capable of reporting the live references or reporting the stripped references after a round of garbage collection. So in this way, we can make the two different heaps coexist with each other. But this is a future extension, and we are going to be implementing this sometime later this year.
Are you talking to Andreas Rosberg about this storage management stuff? Because he's actively thinking about all this and what extensions to WASM. I think WASM isn't a fixed thing; it's a movable thing, and I think they're quite keen for it to be as hospitable a host for languages like Haskell as possible. So they're not going to completely bend it out of shape to accommodate Haskell. But if there are small things like you say, with some tricks, maybe you could formalize the tricks so that they were not tricks; they were just part of the spec. Do you see what I mean? As part of a conversation.
I had earlier conversations with Andreas Rosberg, but that's about using the WASM GC proposal as a backend for Haskell. And eventually we decided that for these weird corner cases for the Haskell mutators, then probably it's not worth the effort.
Yeah, that seems like quite ambitious to use the, a JavaScript or WASM garbage collector. But what you're here saying is we've got a GHC garbage collector.
Yeah.
But it's still quite tricky to interface with WASM. So I'd encourage you to have that conversation with him, because I think he'd like it to be good for that.
Yes, that's a very sensible suggestion. Thanks. On to the next slide. The storage manager part is the most tricky of RTS to port to WASM 32, and there are other parts in the RTS that needs a little bit of twisting and optimization to work on WASM 32. To make something in RTS work specifically in WASM 32, we have to add some conditionals in WASM. There are different ways of saying that I want this piece of code only compiles or runs in WASM 32, but not on other architectures. First of all is autoconf feature detection. So in not just RTS, in libraries like Base and Unix, before you actually build the Haskell package, you have to run an autoconf script. And that script is running the C toolchains to detect a lot of things like, does this header file exist, or does this function exist? So if we want to make WASM 32 extensions to a package, we want to avoid the term WASM 32 in the source code as far as possible. Instead, we want to just assert that, does this functionality exist in the target C toolchain? If it doesn't exist, then we just add this detection logic. And then we are going to be adding the CPP macros, which asserts that if we have some header files or if we have some function, then we do this functionality. So autoconf feature detection is the main effort to make WASM specific logic in RTS. Another thing is last resort. All of the Cabal library ensures that whenever we are compiling a thing with the GHC WASM backend, it inserts the WASM 32 host architecture macro. So this macro can be used as a very easy effort to insert your WASM 32 specific logic in the libraries. And also, if we are talking about Cabal packages, then the latest version of Cabal already supports the WASM32 as an architecture predicate. So you can say that if architecture is WASM32, then compile these C bits. Otherwise, compile those C bits. You can do this kind of things in Cabal. So this is the way to add WASM-specific logic in the different libraries. So first of all, one thing we need to get rid of the RTS is the timer. So Ben actually didn't talk about the RTS timer in the RTS slides, so I can provide a little bit of context here. He did talk about a thing called the run queue, so that the idea is that a lot of the Haskell threads, they are going to be put on the run queue for the capability to actually run them. And there is a context switch flag in the run queue that decides when I want to enqueue a Haskell thread state object, do I want to put it on the front of the queue or the back of the queue? And the different selection here is the different scheduling priorities. So the RTS timer in the vanilla Haskell RTS is just a background POSIX threads that after a fixed interval of time, it always sets the context switch flag to 1. And then when the mutator detects that context switch flag, it's going to be always putting the Haskell thread to the back of the queue. This means that we are doing context switches. We are enabling other Haskell threads for prioritize the execution. And because the WASM32 WASI, it doesn't have a threading model yet. So there is no way to spawn a thread which is specifically resetting the context switch flag at a fixed interval. We just disable the RTS timer. So this is one part in the RTS that we have to disable. And another part is RTS linker, because the RTS linker is...
So is that to say that when does context switching happen in that case? Like, what is the story for preemption? Yeah.
So our choice is that we always put the thread at the back of the queue and delegate to other threads. So it's sort of like the C0 or V01 in Haskell RTS.
So like every heap check, essentially,
yes,
you're going to...
It always do the context switch in order to avoid starving.
Yeah.
Yeah.
I mean, I guess you could also just count or check the time in
yes,
the...
you can proactively check the time in the RTS. In fact, I actually wonder a little bit why we aren't just checking the time proactively and instead rely on a background thread. But yeah, that is not a part of the talk. Yes. Yeah, so apart from the RTS timer, we have
Wait, I think Ryan as well.
I had a basic question about WASM32 in particular. I guess is WASM64, does that enter the picture anywhere here? Do you get WASM6, or is that the next part?
It's in the next slides.
Okay, thank you.
Yeah, all right. So we have to disable the RTS linker also, because we have said before that getting the dynamic code loading in WASM is pretty tricky. And also, there is no thing like preemption from the signals. This is something that exists in POSIX and Windows, but doesn't exist in WASM for good reason. So anything that is related to signals has to be disabled in RTS, and also things related to threads or processes. So, of course, a lot of the Haskell Cabal packages, they just add a threaded flag, which for a good reason when you are targeting Linux, but this is not going to be working for the WASM backend. And also, yeah, we don't have access to TTY or other fancy console features, but this is a limitation not in WASM, but in WASI. So if we are in the future targeting the JavaScript as a target, then, well, we can just use third-party libraries like xterm.js to provide these TTY functionalities and have them as, like, for instance, WASM imports. Yeah, foreign exports. This is worth a standalone slide, but I'm afraid there's not too much time to go into the details of how we implement a subset of libFFI to enable limited functionality of the foreign export C functionality. So what you need to keep in mind is that in order to make the foreign export C feature work, which is just wrapping a Haskell function and making it into a C function pointer so that you can pass this C function pointer to some other C libraries, this feature is deeply rooted in the capabilities provided by the ABIs and your architecture in general. And because of the strict type checking of WebAssembly, it is actually very challenging, if not to say impossible, to implement this properly in WASM32. So we have a limited implementation of it, but it comes with its own limitations. Now, we can talk a little bit about how we lower CMM to WASM. The pipeline is pretty clear. We go from Haskell to core to SDG to CMM, and then we use the CMM as the starting point for the GHC WASM backend to emit the kind of object files that we have described earlier. So how does CMM fit in with the other code? Yes, we can think of each CMM compilation module as a standalone object file that must be capable of linking with the rest of the C world. This means that they have references into each other. The CMM world is able to use the C symbols and make C calls, and the C world may refer to CMM things by their symbols. And of course, execution of CMM code is not just as simple as just coercing the CMM symbol to a function pointer and calling it. You need to set up various contexts for execution, capabilities, tasks, things like that, which has been described in the previous talk. And the CMM world has a single entry point which jumps to the top of the SDG stack for execution. And it has a single exit point called SDG return, which just cleans up everything and returns a null function pointer to indicate that everything in the CMM has finished execution, and we are yielding back to the host C functions. So the job of the WASM backend code generator is take CMM, generate WASM object file, and the first code generator we are going to be introducing is the unregisterized code generator. So in order to get this behavior, you have to pass a special configure flag to GHC at build time, enable unregisterized, so that it knows to bypass any existing native code generators for your target architecture, and always compile CMM to C, and then uses the C compiler to compile that C file into the native object files. And in terms of the WASM32 target, it is pretty slow, both at compile time and at runtime. It is slow at runtime too, because if you have to target C instead of targeting native assembly, then this actually limits your capability of doing things like lowering the CMM global registers to machine registers. You can't actually do that. You have to lower these things to less efficient constructs. So yeah, the WASM backend's unregisterized code gen is not recommended for typical usage, but it is useful in a sense that when we are debugging the native code generator, especially in the early days when I was rushing to get this merge request approved, it can be used as a source of truth because it's possible that I have some hidden bugs in the native code generator, which makes a weird runtime behavior. And I can just try compiling the same program with the unregisterized mode and see if it still has the same bug. So it is useful as a source of truth. Now, we can introduce a little bit how the WASM backend's native code generator is working. It generates the textual assembly format from CMM directly. It's the recommended approach, by the way. Yeah, we are going to be giving a quick tour of CMM probably. In order to have some idea what kind of CMM we are going to be working with, we need to gather some examples of CMM. So there are different ways of gathering these examples. One is that you can look at the .cmm files in the GHC source tree, especially in the RTS directory. And also, when you are compiling a Haskell module, you can attach these GHC flags, dedump to files, dedump CMM raw. Notice the raw suffix, because there are actually two different flavors of CMM coexisting in GHC. The higher level CMM is more like C syntax in that you can write the arguments in, you can write an argument list, and then you can return some value from the CMM. But this high-level CMM is going to be lowered to a variant called raw CMM, in which all of the argument and result passing has been delegated to the global registers like R1 and such. And the CMM, the WASM generator is taking the raw variant of CMM as the starting point, in which all of the heavy lifting has been done by the GHC. When we are learning about the CMM internals, we have to keep in mind that the textual syntax of the .cmm files is actually just a subset of all the CMM AST, which is defined in the GHC tree. And unfortunately, the CMM dumps isn't valid syntax. So if you dump CMM from Haskell and then you try to recompile that CMM file, that is not going to be working. The canonical reference of the CMM AST is the GHC.cmm module that you can take a look later. We don't need to go through everything in the CMM AST because that is not going to be fitting in this entire talk, but we are going to be focusing on some interesting things to look on. The first thing that we need to keep in mind is the CMM symbol type C-label. So one property to keep in mind about C-label is that when we pre-print to the assembly file of the target architecture, it performs Z encoding, which is already described in the previous talk. So because the C toolchain, the linkers, they have some limitations about what kinds of characters may appear in a symbol name, so that some of the characters are replaced with the Z-started characters. So don't be too surprised if you look at a CMM dump and then you see some Z-encoded symbols there. And C-label doesn't just carry the string. It also carries some metadata that will be very important when we generate assembly. For instance, we need to know one entity which is it a code entity or is it a data section? And of course, we also need to know if this is something that is defined in the current module, is it only visible to the other entities in the current module, or is it externally visible? This is something that we also care. And in CMM, there are two kinds of things, code and data, of course. The data part is really the simple part. There is not much to say about the CMM data sections, except one thing, alignment, because most kinds of the CMM data sections, be it info table or the static closures or things like these, they have to be word aligned, and otherwise you're going to be getting a misaligned memory access. And what is worse, GHC has different kinds of pointer tagging tricks, and these pointer tagging tricks will require that your pointer has some idle lowest bits for pointer tagging. And in order to make those tricks work, you have to make sure that these data sections are word aligned. Well, one exception to that is the string literals, because if you're emitting a string literals, then there is absolutely no alignment constraints to these kind of things. Now, the CMM data, there isn't much to talk about. But when we talk about the CMM code, then just like the WebAssembly, CMM itself has a type system. And it's actually a little bit richer than the WASM type system because there exist types of subwords like the 8 bits or 16 bits integers. And these things are used to implement the arithmetic for the primitive types like words and integers of the 8 bits or 16 bits. And another tricky part of the CMM type system is that although it tracks the sizes of this type accurately, it doesn't actually track the signedness. And this can be pretty tricky when you are doing subword arithmetic and some of the operands are loaded from memory. If you forget to do some like sign extension or zero extension, if you forget these kinds of operations, and then this is going to be resulting in very weird runtime behavior. So you have to be extra careful when you are dealing with subwords in CMM. You have to keep in mind whether you need to do zero extensions, signed extensions, or truncations at the right side. Now, in CMM, there is a clear distinction between expressions and statements. So there is a CMM expression type, which conceptually, we can think of them as some operand that is free from side effects. And whenever in CMM we want to cause some side effects, like calling a foreign functions, or are we going to be assigning CMM expressions to some locals, then we are going to be having a CMM statement, which is called CMM node. You can do these kind of things. And in CMM, just like WASM has local and global in CMM, we also have the local and global virtual registers. Ben has already did 9 introductions on how the global registers like R1, R2, they are used to pass the function arguments to the CMM functions. And there are also special global registers like the heap pointer, the stack pointers, or things like these to maintain the consensus between the mutator code and the Haskell RTS. So yeah, these are the virtual registers. Each CMM function is a control flow graph with a special entry label. So this will become a little bit tricky to lower the control flow graph to the structured control flow as described earlier. And there has to be a special algorithm to take care of this. Now, the function calls between the CMM functions are always tail calls, but you just said that there is no tail call implemented in WebAssembly right now. So what kind of tail call are we talking about? So there are actually, apart from the value stack in WASM and the control stack, which is the WASM or C call stack in WASM, the third kind of stack we are talking about is the Haskell stack or STG stack. Yeah, it is a first-class heap object managed by the Haskell garbage collector. And of course, you can grow the STG stack or shrink it appropriately at runtime. And when we talk about CMM tail calls, we are saying tail call in a sense that it never actually grows the native call stack. It doesn't grow the control stack, but it's perfectly possible for a CMM function to push something to the STG stack and grow the other one. Yeah. So each CMM function call has to be a tail call in order for the correct semantics at runtime. Now, if we want to compile CMM to WebAssembly, we need to generate the assembly textual format, and we have to learn a little bit about the textual assembly format. One way to do that would be using CLang to target WebAssembly, compile some small C examples, and pass the -s flag. So the -s flag, it tells the C compiler to not generate the object code directly, and instead generate the assembly code. So you can compile some small examples and learn through these examples. It's pretty straightforward. And there are also, of course, existing cases in the LVM source tree, and you can search for the .s files in the LVM repository and look for those things that are related to WebAssembly. Well, I gathered all my knowledge about the WebAssembly assembly format by just learning through these examples. So. And in order for these assembly files to actually generate correct code at runtime, there are some tricky parts to watch about. So first of all, you have to get the symbol visibility right. So if you're generating a data section or a function and you want it to be visible from other object files, then you need to emit special directives in the assembly file to tell the linker to do that. And of course, we have spoken earlier that the WebAssembly has a strong type system, and in order for the function calls to be correct, you have to always accompany the function symbols by their correct type signatures. And it is not always straightforward in CMM to do this, because the C label type, it doesn't always carry the C function signature. So we have certain tricks and gimmicks here. So for instance, if a C label is mentioned in the context of a foreign call, we are sure that we are calling a C function. Then of course, in the foreign declaration, we already have the arguments and return values. Then we can perform a very limited kind of type inference. Then we can infer the WebAssembly type of the C function to be called, and then we can put that in the target assembly code. But if we are sure that something is a function, but there is no such thing as a foreign C declaration associated with the C symbol, then we fall back to the assumption that it is a CMM function. And then we use the fallback function signature to decorate the symbol. And yeah, this sounds a little bit tricky, but it works in practice.
It's actually quite interesting because the LLVM backend has to deal with a very similar issue. And we use, we have a very horrible hack for dealing with this. We essentially erase the type information and coerce the function to the to sort of a placeholder type.
I think you're actually talking about the unregistered code generator.
No. Well, I mean, perhaps as well, but which is also true, actually. Yes, that's true. But no, the LLVM backend definitely. It would be very interesting to apply this technique and rip out the the Alias-based approach in the LLVM code gen. Less of a question, more of a comment. Sorry.
It's all right. Yeah. And last of all, the WASM linker, unlike linkers on other architectures, has zero tolerance about the confusion of the symbol kind. If you refer to a symbol, you have to be explicit whether it is a data symbol or a function symbol. And unfortunately, the C label metadata about whether it is a function or it is a data is not 100% accurate. And I have run into some weird issues when the linker complains something is a function where in fact it has been a data symbol. So the way that we mitigate this problem is that we go over all the handwritten CMM files in the RTS directory. And whenever we see that this is something that clearly refers to a data symbol, then we add the import closure declaration next to it. So to guarantee that when GHC parses this CMM source file as in-memory CMM, this symbol kind is already corrected. Yeah, there could be alternative approaches like guessing from the symbol name. If it has a suffix called -info or -closure, then we are sure it's a data symbol. But that is an even horrible hack.
But symbols kind is the only way this goes wrong. Like okay.
Yeah, it's the only thing that goes wrong, and yeah.
Oh, that's good to hear. Okay, all right, yeah. Oh.
Yeah, so these are the things we need to know for the correct generation of assembly code. And some of the backends for other architectures, they just pre-print to assembly directly. But we don't do that. We actually just build an in-memory representation of the WebAssembly code first, and then using that representation, we generate a assembly file. All right, we have to speed up for the rest of the slides, so we are not going to be going into too much details here. What you need to know is that the word that you're looking for WebAssembly generation is WASM codegen M. It's a pure state monad, which collects a bunch of metadata. So we go through all the CMM declarations in a single pass, and then we populate the state by the WebAssembly in-memory representation. And then, yeah, this is how we do it. One thing that I'm very proud of, but I'm afraid we don't have too much time to cover, is that we use dependent types to some degree to track the value stack in the to track the WebAssembly IR. The basic types are the 4 value types in WebAssembly spec. The WebAssembly IR, everything in the WebAssembly codegen has a type variable W, which stands for the word length. So in the future, when we emit code for the WASM 64 target, as Ryan has just asked earlier, then we can reuse almost all of the codegen logic. Just instantiate the same terms with the different type variables, and everything just becomes 64-bit out of the box. Yeah. And we use type level list of the WASM type to stand for a value stack. So all of the WASM instructions in the WebAssembly native code generator, they always take the word type as a type variable, and we also take the pre-type and post types. So the pre and post stands for the value stack types. And whenever you want to lower a CMM primop to WASM operation, you have to convince the Haskell type checker that you are lowering to the correct type signatures. Otherwise, you are going to get a compile time error. So yeah, this is our basic approach. We also have some wrappers for all and existential wrappers around the WASM instructions for convenience. Like a WASM expression is just something that always spills a single value on the value stack, and a WASM statement is something that doesn't touch the value stack at all. So yeah, this is a pretty neat usage of singleton types to do this kind of WASM modeling. The rest of the CMM to WASM story is pretty straightforward. CMM symbols, we just convert them to the Z encoded forms. Each CMM local register just becomes a unique WASM local register. CMM global registers are either lowered to a WASM global, which is slightly more efficient than just loads and stores of linear memory. But in some cases, the C code in RTS also needs to manipulate these registers, in which case we just fall back to the slots in the register tables. CMM expressions, we just build up the WASM instructions in memory. And in order to lower a CMM control flow graph into a structured control flow, we need to go through a special relooper algorithm. So relooper stands for regenerating code with proper structured loops. So this part, my colleague Norman Ramsey knows much better than me. So you can check out his ICFP talk and paper, which is linked here. All the CMM tail calls in the end, we are lowering them to trampolines by default. So each WASM type signature of a CMM function is pretty simple. It takes 0 parameters and returns a function pointer, which is going to be the callee of the current CMM function. So we just return the function pointer here. And it is possible, as of today, to generate code for WASM's native tail calls instructions, but that takes special build time configurations, which is already described in the GHC.-wasm-beta repository. So yeah, this is how we do the code compiling. The pretty printing, there is nothing to say about the pretty printing from the in-memory WASM IR to the final assembly text file, because it's very simple and we don't do any pretty logic. We only consider the indentation of the blocks. So yeah. Now finally, the final slide is about testing the WASM backend. We already support using the Hadrian test command to run the entire GHC test suite to test the WASM backend. The secret of this is the cross-emulator environment variable. So there is a convention that once you run Hadrian test, you specify the cross-emulator environment variable to something like WASM time or user mode QEMU. It takes the target executable and then wraps it and runs it as if it is a native executable. So it's already supported as of today. We can also go over the final slide, how to debug the GHC WASM backend. So first of all, we have, because WASM is a pretty young platform, I have filed quite a few CLang bugs. So sometimes it's not really your problem, right? So you can try different WASM runtimes or different optimization levels in CLang in order to see whether the same bug is still manifesting. And if you're sure that this is indeed our problem, then first of all, you want to make the runtime failure crash as early as possible. The way you would do this is to use the debug variant of RTS and enable all sorts of sanity checks, so to move the crash site as early as possible. Now, another tool I want to mention here is C-reduce. So C-reduce is a tool that it takes a C source file and it takes a shell script that observes an interesting property with that C file. For instance, it crashes the C compiler or it crashes the WASM runtime with an interesting error message. Well, you write a bash script to test for this property, and then you use C-reduce, and then it automatically deletes the irrelevant parts of your C source file and get up with a minimal repo. And despite the name, it can actually reduce everything that is textual: C, assembly, Haskell, even bash scripts, and of course, including the WebAssembly textual format, as we described earlier. So once we have the C-reduce weapon in our weaponry, we can, when we have a GHC invocation that is, we're absolutely sure is having a buggy behavior, then we can pass the keep temporary files and verbose flags to GHC so that we can see what command is actually linking the final WebAssembly module. And then we try to find a way to see which library is actually the crime scene. And then we narrow down our crime scene to a single object. We obtain the assembly code of that object, and then we use C-reduce to shrink the assembly code of that object to the point that the bug becomes self-obvious. Yeah. There are also tips for efficient C-reduce usage, like you almost never want to rename any tokens in the input source file, because it's unclear. If you rename some of the tokens in the input source file, then it is unclear which symbols they actually are in the original source file. And also, you want to kill the test process as early as possible, because in a lot of cases, a C-reduce will provide some weird outputs that will make the CLang or the WebAssembly runtime spin infinitely. So yeah, these are the tips. And you want to use a fast runtime for running the WASM repos. So yeah, these are pretty much everything I need to know about debugging the GHC WASM backend.